Look at the sign. It says metamorphic minerals, and I have to say there's so many. If you start to look them up, don't press your print button, because you'll end up with 90 pages. That's dangerous. So actually, my talk is not on any particular mineral, but the environments that they occur. So this way, if you know you're in that environment, you know what to look for. So that's basically it. Okay, so what are the three basic mineral groups? Rock groups.
Sedimentary, metamorphic.
Keep going. Right. So it's MIS, metamorphic, igneous, and sedimentary. Which is the first? Which comes first?
Sedimentary.
Incorrect.
From
Igneous.
the top or from the bottom?
Yep, the igneous comes first. Because when the Earth was first formed, it was all liquid. So the basic groups are separated based on how they form. I guess that's a simple way of putting it. So if you're igneous, you're forming from a liquid. If you're sedimentary, you're forming from previously existing rocks that broke up and got re-cemented or joined together again. And the metamorphic are those that form a different way. So that's what we're into. Let's see. Can I do this? Metamorphic minerals. Okay. So we're going to begin with the first question. What evidence can you cite that the crust of the Earth has moved? Name something that told you that the Earth's crust moved. We have evidence. And it says there are 8 answers, probably more.
Mount St. Helens.
Mount St. Helens? Okay, with volcanic. Okay, so if a volcano moves, it moves material from one place to another as a liquid, but it tells you that the Earth's crust moved. What else?
It looks like the Horn of Africa meets with part of North America.
Okay, so he's saying,
tectonics.
what would we call that?
Tectonics.
Tectonics, okay. Or maybe, is it
Plate tectonics.
Plate tectonics, or there's another word for it.
History.
Okay.
Earthquake.
Okay, earthquakes is another. Something else.
The Hawaiian Island chain of volcanoes.
Okay, the chain of volcanoes. The volcanoes keep popping up in the same place, which means the crust must be moving over it and producing that feature. Anything else?
Mid-Atlantic Ridge,
Mid-Atlantic Ridge. Well, how is that a sign that?
because it's pushing Europe and North America apart.
Okay, so again, it's the separation of the continents.
Subduction.
Subduction. How do you prove that? You can't even see subduction. That's a theory.
Mount St. Helens.
That's a theory. Okay, what else?
Yeah, reefs and falls.
Faults. Okay, you see things being displaced, right? That's what a fault is. It's a break along which movement occurs. Tell me something. If you have a break and there's no motion, does that mean the Earth's crust moved?
Well, how about the fact that you find fossils on the top of Mount Everest?
There you go. Fossils on the top
They move up.
of a mountain. How does it get up there, though? Fossils crawl up? Okay. Do
Well,
sharks
they
have
were
feet?
sea fossils.
Okay. You find-
Anticlines, synclines.
Okay, folding. The Earth's crust folds. Okay, so that means it's moved. Something else. Anything else? Look at how much evidence we have.
Impacts.
Say again?
Impact of asteroid.
An impact of an asteroid?
Yeah,
But
potential.
that doesn't have the
Does that mean the Earth's crust is
In
moving? That's making a hole in the crust, but doesn't mean
in
the crust.
craters.
Oh, craters. Okay, you're throwing stuff around. Okay.
Mass
No,
wasting.
It's
That's
lazy.
very local. Very local.
Of
Okay,
course.
anything else?
Mass wasting.
Mass wasting. Okay, that's movement across. Yes, that's a whole topic in itself. Mass wasting. Most of you may know that as avalanches, mudslides.
Rock slide.
Say again?
Rock slide.
Rock slide. Okay.
Slumps.
Slumps. Okay. Wow, you know a lot. You're gonna come up with solar fluxion? Oh, that's a good one.
Oh, yeah.
All right. Anything else? We ran out of things. Come on.
Big fires.
Big fires. No, fires. How about the fact that you have all these marine sediments at the top of a mountain, maybe 15 kilometers worth? How'd they get up there?
Tectonics.
Okay, it's a sign, it's evidence that the crust moves. So we know the crust moves, and it's because the crust moves that we produce what's necessary for these minerals. Let's see if I can do this again. All right. So the Earth's crust, we can go over to earthquakes, volcanic eruptions, displaced structures, which are called faults, benchmarks that change values. That's one we didn't mention. Everybody know what a benchmark is? Okay, you look at a map and you see a little triangle with a dot in it, and it'll have a number next to it, and that will tell you the height at which it was measured above sea level by the Geologic Survey. That's called a benchmark. And if you're looking at topographic maps, you see a lot of those, but they do change.
Well, now we have the GPS.
I know because I worked for the Geologic Survey, and what I did was go around and check the benchmarks to find out what the elevation was from their new maps. They would give me a map that was readjusted, and I would go there and see how far off it was. In fact, I was also finding elevations of libraries, police department, all kinds of things municipal oriented. Okay, we also have tilted and folded rock layers. We got a lot of these, right? Sedimentary rocks above sea level, marine fossils atop the Himalayas, those are the crawling sharks, and sea sediments 15 kilometers thick atop mountains. There's a lot, and there's more. So we know the crust moves. Okay, good. All right. Wow, that's evidence. Boy, that's a lot of evidence. And you could probably pick out a few of those things that happened here. Can you see a fault? See a break with a displacement?
Yeah,
Can you see any folding?
yes.
You could see motion. Can you imagine what could have caused this? And of course, it might have happened all at once, like a catastrophe, or it might have happened very slowly. We don't really know. There's a lot of theories about how long things take, but you can see that there's been a change. Okay, and this is a sign that you're in a metamorphic environment. All right. Oh, that was good. A little faster? All right. So, what is metamorphic? Well, it's a process that actually changes the structure of a mineral by using pressure, heat, and chemically active fluids, and it's still in the solid state. Still solid. Okay, and these environments occur deep within the earth, because as you get deeper in the earth, you've got more weight on top of you, right? And that presses down, and that's going to give you the pressure and heat. Because remember, anytime you press things together, you generate heat. Think of making a snowball, right? When you make a snowball, the heat of your hands presses the snow together, and doesn't the snowball melt a little bit? And then it gets a shiny look on the outside, and that's the sign that compression will create heat. And the weight of material on top of you is always pressing down, and the deeper you go, the more pressure you have, the more heat you have. All right. Near volcanic bodies, well, that's heat itself, right? Because volcanoes are pretty hot stuff. And in areas which have been involved in regional uplift or tectonic plate movement, areas where they're being moved. Actually, faults actually have places on them where the rocks slide against one another and generate friction, and you end up with heat. Okay, metamorphism. Notice it said in the solid state, right? Could it have been, can you generate enough heat to melt the rocks?
Yes.
Okay, once you melt the rocks, it's not metamorphic anymore. Why?
Changes natural state.
Going back to igneous, it'll become igneous.
Right, it becomes igneous. See, igneous rocks are the rocks, that's when we started that way. Igneous rocks are rocks that are generated by melted rock. So you could see, if you generate too much heat, you make igneous rock. So you're changing the family, its origin. Isn't that neat? You can go around in circles,
What about the opposite?
like most of you do anyway.
Professor,
All right, now, this is a picture of the Earth's crust. The Earth's crust changes. It gets thin over the oceans, and it gets thicker over the continents. Why is that? Because material starts to gather together from the liquid state of the Gesundheit. All right, this is the thick part of the crust. If I were to locate this somewhere, I would say this is Los Angeles over here. Los Angeles is on the west coast. This is a west coast picture. The mountains here, these would be the Rockies, and these go back into our breadbasket. And you can see that the crust is thicker under the mountains and thinner under the oceans. Okay? And you can see this picture shows there's a movement, a general movement in a kind of circular fashion. The magma here is rising, this goes up, this stuff comes back down into the ocean, it erodes, materials get laid down in layers, and then this material is being brought down. That's what the Art mentioned. He said subduction. That's a theory because we've never seen it, right? It's movement of material going down, going so deep it becomes melted and then it rises again, because melted material is lighter than solid, right? It's like pressing down, and it's what pushes the volcanoes up. So it's kind of moving around, and you get metamorphic environments here, because you get heat, pressure, and chemically active fluids, all of them. Once it melts, it's igneous. So this is all happening in the solid state. It's really hard to envision that it's something is solid and the atoms are moving around. Okay. Now, the heat and the pressure of metamorphism actually changes a mineral's structure. It takes atoms and moves them around so it becomes something else. It can change the mineral's chemistry because you could take an element off and add another one on. And all kinds of things happen in these environments. It's under pressure and motion occurs. It's not a liquid, but motion occurs still. And it can produce a new mineral unique to that environment. So places where you didn't have a mineral before can then be generated because the chemistries are readjusted. Okay, it's all in the solid state. We answered that question, right? Because if it was liquid, it would be an igneous rock. Okay, so the next thing is to how do you recognize it? Okay, this is the first thing. You look for banding. Okay, this is banding. Does it look like layers? But layers are different from banding. See the question? What's the difference between banding and layers? Anybody know?
Layers are sedimentary. Layers are sedimentary.
Layers is
Banding occurs because the atoms of the minerals are exchanged and they separate out within the rock.
You got it. Okay. Essentially, what's the difference is a layer is continuous. Like sediments. When sediments are laid down, you lay down a whole bunch, and it's a boundary layer, and the boundary is continuous. If you look at this, which is metamorphic, and you follow a line, it'll stop and go. That's banding. Your eye is caught and sees the alignment of the material, but they're not really continuous. If you follow any one of these things, it's stop and go. That's banding. There's an alignment that takes place in metamorphic environments that your eye can see, hopefully. Not all the time, because this is produced by different minerals. If you have a black mineral next to a white mineral, you're going to see that alignment a lot easier than if you have white, 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 and white, because you can't see that alignment that occurs. But you can see that in this. Notice you also have a lot of distortion. Right? All the layers that's being pressured, and that's what causes that amazing thing. What happens in some of these cases is you get zones of greater pressure and zones of lesser pressure, and the ones where the pressure is lesser will absorb materials from the greater pressure area, and you'll get a migration of material. That's how you sometimes get beautiful things like emeralds, because a zone will be put in. You get structures called boutonage and all kinds of weird things that we've discovered in the metamorphic rocks. There are people who just study this kind of stuff. They're called hard rock scientists. If you're doing fossils, you're in soft rock, because fossils are in sedimentary, easy to break. Metamorphic are tough, because they're formed under pressure, and if you want to start getting minerals from metamorphic, better bring a heavy hammer. The heaviest hammer wins. That's what we usually say. So you can see that there seems to be like a movement of material, and you can see that there's a lighter area here. See it? See, it's much lighter material. Lighter material means lighter in density. It's a less weighty kind of mineral. But notice you also have these little red spots. See them? There's a little red spot here. What is that little red spot in this little place? And then there's a couple other little red spots in places. It's another mineral being formed, and material is being moved to that area because it's got lesser pressure. And that migration of material produces new minerals in different places.
So those be garnets that are happening there? Or?
It could be. The interesting thing about garnets, and someone could do a talk on this, because garnets have a big family. Garnets form in all rocks. They form in igneous, metamorphic, and sedimentary. So that's been a question scientists have had for a long time. Why is it that garnets form in all that? So that's an interesting study, just garnets. So that's, again, a talk for someone else to do if they want to do something on garnets. And garnets are interesting because their colors are beautifully intense, and they come in all colors. They're rainbow. Okay. I have black garnets called melanite, and raspberry garnets, and every color. It's nice. Garnets are a good thing to work. All right. What happens from the very beginning? You take any kind of material since the Earth started as a liquid, and you crystallize it. The crystals will be pointing in all directions, and then if you put this under any kind of pressure, notice what happens. Not only will the minerals change, see they have new minerals, but they'll start to align themselves in the opposite direction of the pressure. So this is the stress, north and south. I forgot to bring my pointer. North and south is the stress, and the release is the strain. Stress, strain, and the strain is the direction where the pressure is released. See it? So you get banding because of that pressure. And the banding is the key to looking and finding metamorphic environments. Got it? Nice. Pretty good. A and B. Can you do this with anything else? Yes. You can do sedimentary material. It doesn't have to be igneous. You could start with sedimentary and put that under pressure, and you'll get metamorphic also. Can you take metamorphic and put it under pressure? Yes, you could do that too. Okay. Yes.
Quick question. I just read in one of these booklets that actually metamorphic structure could be the result of igneous rocks as a source. So
Sure. That's what I started here. This is igneous. You squeeze it, you get metamorphic. You take sedimentary, squeeze it, you got metamorphic. Yes.
The igneous rock can
Question?
heat the surrounding rock and make it metamorphic.
Are there
I
different
think
kinds
that's what you might mean.
of minerals that are formed based on the heat and the pressure that the rock is exposed to? So does it run through, say, the slate, which is a very fine crystal metamorphic rock, through schist, which is a larger, maybe a larger crystal, into gneiss?
Everything
Are those-
depends on what elements are present. If the elements are present there, you can get it.
Yeah, basically sedimentary shale becomes slate, which becomes.
We're getting into
filate.
that.
Yeah.
Okay. That's regional. Okay. All right, moving on. Okay, so this is gonna happen. Hello. All right. Little picture. What area is that? It's a beach area. How do you know the size of the rock? There's people. Always put something in your picture that's a known size. Makes it a lot easier. I mean, if you're looking at a tree, even the tree could be this small. Put something in the picture of a known object. Okay, so can you see folding?
Squashing.
See it?
Yeah.
Can you see something that went down and up, but the folding was so tight, it looks like layers, doesn't it? And actually, if you follow some of these lines, they'll be stop and go. You really have to get close to it. But look, right here, goes down and back up. Right here, this dark area stops. It's the bottom of a fold. Folding can be up and down, that's called an anticline. Folding can be down and up, a syncline. Or you can have a complete fold, down and up. And here, it's so tight that it's hard to imagine it being
What's the difference between
metamorphic.
What the difference between this kind of you call it fold? What about trenches? Not trenches, cracks. I forgot the other word.
Fault.
Is that a question?
In glaciers.
Glaciers?
Crevasses?
What's the difference between crevasse and this fold?
Produced by a different reason. Crevasses are formed because of extension. The glacier is actually moving and the material is brittle. So if you move it, it's opening it up and you're getting the breaks in it. That's not the same. Not the same. Yes?
If you have folding, does that mean it's metamorphic, or could it just be sedimentary rock that was folded but not put under enough pressure to become metamorphic?
Exactly. Just depends on how much pressure. If there's enough pressure, it becomes metamorphic. Sometimes you can get folds, gentle folds, and it'll still be sedimentary. Just means they're moved.
Pennsylvania is folding.
Yeah, a lot of Pennsylvania is folding. We have what they
It's
call
not
rolling
metamorphic,
hills.
but it's not
The
metamorphic.
tops of the mountains are quartzite, that's metamorphic.
The rocks will change as you go from the lesser compression to the greater compression. This is a shale, a slate, a schist, a gneiss, and then, what's that called? A high grade. What happens is that you can tell how much compression has been applied to the rock based on what you see. So you have to get to know the difference between the different varieties. I neglected to bring that with me because there's just so much with metamorphic, but if you want, we'll bring in samples of all of these so you can see the difference between them and you can see the difference between how much pressure changes it. Even in the schist family, you have different amounts of pressure and it changes the minerals in there. For instance, the first schist that to form after the slate is called mica schist. You see actual pieces of mica in the schist. If you continue to pressure the mica schist, it becomes garnet schist. Garnets appear. If you pressure the garnets, they become elongated into what we call staurolite. So you have staurolite schist. If you pressure that, it becomes even longer. It's into sillimanite schist. So you could tell mica schist, staurolite schist, sillimanite schist, garnet was in there somewhere. And then you're actually seeing a greater amount of compression, and the mica seems to, the schist, is the mica part, stays pretty much the same
It's biotite
until it
schist?
becomes totally obliterated, and you get these elongated minerals that look like pencils, and that's where you get gneiss. Mica is a flat mineral, and so when you take flat shapes and put them together, they lay together. Like if you think of I guess you could say paper. You drop a whole bunch of paper. All of the pages are all laying in the same direction, right?
It's cleavage.
If you do that with pencils, will the same thing happen? But you can squeeze pencils, and their direction will start to align, won't they? If you squeeze paper, same thing. They align. So the difference between the schist and the gneiss is that these are flatter minerals, and these are more elongated into pencil shapes. So that's basically, when you're looking at it, you'll see it. I will show you examples. Yes?
Isn't mica the real thin sheets of cleavage? I think I mentioned it.
You're looking at cleavage, yes. But remember, mica crystals are different. Mica crystals are bulky.
Oh, see, I'm thinking, because remember I said, isn't mica what's used for the base burners? They burn,
Yes.
and
That's a mica cleavage. Mica crystal is different. It's hexagonal, and you don't see hexagonal too often. Mica crystals are kind of rare.
The big mica they get like that usually is in pegmatites, which...
If you're lucky, you see a crystal. Sometimes you don't.
The stuff in Connecticut is pegmatite. That's where the big micas form, which, that's really hot fluids that come into the rock from volcanic kind of stuff. Hot environments, but, it's a little different. I mean, it's the same mineral, but just it formed a little differently.
Forms differently because what's...
It's hard to tell you about mica crystals unless you have one to show.
Yeah. The mica then forms from a liquid, from the lava. you know, from hot liquids that go through versus, like he said, versus solid reorganization of something that's already solid.
So this is an example of how metamorphism changes over a large area. Okay, the intensities, it's being pushed against something and it's more intense there, less intense here, and it's just a gradual change, and you see that in the rocks. The rocks tell you where you are in reference to pressure. And that's, all of these are all metamorphic. Okay. This is a kind of metamorphism which consists of, basically in this picture, two kinds of minerals, the white and the dark. Okay, white, remember, are lighter in density, darker, heavier in density. Look what happened. When this got squeezed, they didn't all seem to follow the same pattern, did they? So darker minerals appear to be different than the lighter. And you can see that the undulation back and forth is different for darker and lighter. These are called migmatites. Okay, and of course, we passed one a second ago. It was just a light touch, is that you also get metamorphism from being close to a magma source, like a volcano. So if you have rocks being extruded by volcanoes, the magma being close to the country rock outside will become baked and made into metamorphic too. So that's called contact metamorphism. So there are three kinds of metamorphism here so far. The regional, over a large area, the contact being close to a volcano, and the, what was the other one? The migmatites, being that when they're squeezed, they all behave differently because of their density. Question?
We're 20 miles from slate, which is a metamorphic rock, I guess.
Yes.
Does that mean there are other metamorphic rocks around besides just what we find in Bangor?
What happened was you have this place was all underwater and mostly shale, and the shale got squeezed by the undulations of the folding and made into slate. But I haven't seen anything greater than that until you get to maybe closer to Philadelphia.
Well, C.K. Williams is marble.
Is what?
Marble
Oh,
and
right.
serpentine, that's
Right.
metamorphic. So
That's-
that's from limestone.
Still closer to. It's going south. Going south, you get
And all of Franklin,
That's,
that's all metamorphic.
all the
That's-
serpentines. All the serpentines.
And
Right.
the serpentine belt goes all the way from New York State through Franklin through C.K. Williams down through, just outside of Reading. I mean, that's all.
The New England states basically have a giant regional morphism, and the most intense is right by New York City. That's why New York City has such tall buildings. It's so intense underneath. It's very strong rock. And of course, geologists who collect rocks like us, rock hounds, as soon as they see them building a new building and digging a new basement, everybody is peeking through the holes through those fences. They want to see where the trucks are going, taking all the debris. And the trucks have been taking all the new building material, or I should say the crust material from the buildings. They're dumping it into the Hudson River. And you used to see these rock hounds wading into the water to grab anything they can, because the gemstones being dumped by these trucks, because the truckers don't know anything. Yes?
Professor, about Manhattan. In Greenwich Village, I heard there is voids actually in Manhattan basement rocks. In other words, there is empty spaces also.
Voids?
And this is why they don't build skyscrapers in the village, Greenwich Village.
I haven't heard that, but it's okay.
But the Midtown is skyscrapers and downtown.
Where do you get voids in a metamorphic region? How do you get that? Usually it's tight.
No, it's not metamorphic, it's granites, it's igneous.
Yeah, it's igneous,
It's igneous in Manhattan? Boy, I didn't learn that.
Yeah, it's igneous. Granites in Central Park, it's granites.
Usually
I was
the,
gonna ask you, isn't granite?
I'm not familiar with that.
It's igneous.
The Palisades and all that is all igneous.
Yeah.
Right, yeah, but that's not in Manhattan. It's New Jersey.
Yeah, but
Isn't that-
there's a lot
Why, some of it got into Manhattan?
Another talk.
It's another talk, all right.
And we're talking
But no
igneous.
skyscrapers in the middle of Manhattan. Only
That's because it's
uptown
Central Park.
and downtown.
You need room for the people. Okay, these are pictures of rocks. There's a penny here just to give you some idea of size. Can you pick out the metamorphic ones?
Banded ones.
The banding. Can you pick out banding?
Yeah.
Can your eye see banding? Take a look at this. Does your eye see an alignment in there?
No.
Anybody?
No.
You know, sometimes people do see things. Your brain does some strange things. It can actually create alignment in patterns. Okay, so you could tell that some of these are not metamorphic. That's good. That's good. Good samples. Wow. Notice lens cap. That's important. So you know how big this is.
Yeah.
Wow.
Felt thinking that.
This is I forget what this was.
It's a garnet. It's a
Used to
garnet.
be layers.
But that's a nice round garnet.
That's a good try. Good try. Wow, this is amazing. The movement of the material is just amazing. And you can see, can you see any faulting? See anything look displaced? It very commonly happens because it's under pressure and you could slip and break. Anybody see it?
Mica involved, yeah.
Upper left there.
Upper left?
I see it in the lower, that lower bottom.
There's a break right here.
Yeah.
See it?
Oh, a little break, yeah.
And the break happens along the banding.
Yeah.
And you got to say that a lot of this looks continuous. It looks continuous. If you follow this, it looks like it's going in, but eventually it just disappears. Amazing. And is it easy to look and see where there would be greater pressure and lesser pressure? Can you see? Because the places where there is lesser pressure is where fluids would be migrating,
It's
and
like looser.
metals, dissolved metals might migrate to that area where you could find things like platinum, expensive metals, because they migrate in these environments if they're present.
Felsic layer would be feldspar or as a
Feldspars are the lighter colors. That's called felsic. All that family of very light minerals would be that. It's just a beautiful picture. All right, so what do we start off? We start off with, this is sedimentary. How do I know?
You see crystals.
There are no crystals here.
See the,
There's a penny. No, that's a dime. I'm sorry.
it almost looks like ripples or, you know.
Yes, those are ripple marks.
Ah,
Ripple marks happen right off beaches. And this is sedimentary, ripple marks. They're continuous. And this is, as you can see, foliated and has banding. This would be called a gneiss. This would be called a shale. You could take this, squeeze it, and become that. Good. You could also become other things. All right. This one, you see the difference. All right. All right. So now you take all these rocks that become squeezed, call them metamorphic, and they can be divided into three groups: the foliated, the lineated, and the massive. All right. Foliated means the particles are like plates. Lineated means that the particles are like pencils shaped. And massive means there's no differentiation in color, so you can't see individual, it's very hard to see individual crystals unless you're looking at the shape of a cleavage. Because as you turn the specimen in light, you'll see a sparkle. The size of the sparkle is the size of the grain. Okay? So you can get fine grain marbles or coarse grain marbles. Okay, and that's what you have. So we have these groups of rocks. All of them are formed under compression, and it says Inequal grains may be aligned to form a preferred orientation. That's what happens. You compress them this way, and they elongate the other
Can you
way.
go back one? Go, oh.
You can take that compression and take your grains and really knock the crap out of them.
Smush the hell out of them.
Yeah.
Can you go back 2 slides?
You want to go back?
Go back 2 slides. I have a question.
I could do that.
One more.
One more before that.
One more before that.
Slow thinker. All right.
So when massive, is that, because we have the quartzite,
Yes.
would that be like the massive? Would that
Yes.
be massive?
Yes. You don't see any lineation. You don't see any banding.
Okay,
You can occasionally you'll see a change in color,
right.
and the color might show you the preferred direction, but you're not. It's all going to be uniform.
Yeah, okay, because a lot of our quartzite on top of the ridge there
Yeah,
is,
yeah.
so that would be a massive.
We have quartzite here, right?
Yeah, on top of the ridge.
Right. We mentioned that before.
The other one, the streams, too.
Which probably eroded
Probably
down.
eroded
Yeah.
from the top of the mountain.
This is another picture showing you the migration of material from the beginnings of metamorphism, just increasing the pressure and the final vision of how minerals separate themselves into bands. Okay, so we take all the banded ones that are foliated with flat grains. You have the slate, the phyllite, the minor schist, variations of schist, sometimes greenstone and hornfells. They're all classified as having flat particles, some very small. The hornfells are very small. The greenstone a little bit larger. Greenstone would probably include things like serpentine minerals and olivine and all those that have a green shape because of the presence of maybe copper. That would give you the greenstones. And there's a lot of them at the C.K. Williams Quarry. The other ones that are banded but lineated would be your gneiss. So, wow, isn't that interesting? We only take one family of rock and put it in a lineated group,